Hi, today we are going to learn about hybridization. Hybridization is a very important concept in chemistry which allows us to predict the geometries of different compounds. Today we are going to learn hybridization using a very simple compound which is CH4. So CH4 is generally known as methane. Now we'll predict the geometry of methane using hybridization. So to do that, first let's look at the electronic configuration of carbon. So what is the electronic configuration of carbon? To write the electronic configuration of carbon, we need to know the atomic number of carbon, which is 6. Now, if I have to write the electronic configuration of carbon, I'll write it as 1s because 1s orbital will be the first one where the electrons will go. So this is my 1s orbital, and let me draw the orbitals also here. So 1s will have 2 electrons. As we learnt in the previous videos, 1s orbital will have 2 electrons. So 1s here has 2 electrons, one of this spin, the other of the opposite spin. So these are my 2 electrons. Now the other 2 electrons will go to 2s orbital. So this is my 2s orbital. So this will be my 2s orbital. Here also I'll have 2 electrons in the s orbital, 2s orbital. So here I have 1 electron, the other one with the opposite spin. Now if we talk about the p orbital, so p subshell has 3 orbitals. P subshell, if I talk about 2p subshell, it has 3 orbitals which are, so this is my 2px, 2py and 2pz. So this is my 2px, 2py and 2pz. Now how many electrons are left to fill? So there are only 2 electrons to fill. So I'll write it as 2p2 and here also 2p2. These electrons will go into 1 into 2px and 1 into 2py with a parallel spin. So this is how my carbon's electronic configuration will look like. Now if we will have to look at the orbitals of carbon in 3D arrangement, how they will look like. So they will look like there will be a nucleus in the center, then there will be a 1s orbital. 1s orbital will be something like this, and we'll have 2 electrons in 1s orbital. And now let me draw 2s orbital. If I have to draw 2s orbital, it will be something like this. This is my 2s orbital and it will also have 2 electrons. So here I'll have my 2s orbital. Now if I have to draw the p orbital here, for drawing p orbital, let me first draw the axis through the nucleus. So this is my x-axis, this was my p-axis, this was my y-axis, and this is my z-axis. So this is my x-axis, z-axis and y-axis. Now if I have to draw p orbitals here, my py will look something like this. This is my py orbital. So this is my py orbital, let's say 2py orbital. And if I have to draw px, I'll have to draw something like this. So this is my px orbital and this is my pz orbital. Now how many electrons do we have in 1s, 2s and 2p? So this is my 1s, this is my 1s, it has 2 electrons. This is my 2s, it has 2 electrons. And in p orbital, in 2p orbital, in 2p subshell we have 3 orbitals, 2px, 2py and 2pz, in which we have 2 electrons. So those 2 electrons will be in, let's say those are in x, 2px and 2py. Now if carbon has to bond with hydrogen, here in methane carbon has to bond with 4 hydrogens. Now for bonding to happen, what will happen here is, in 2s and 2p, this 2s electron, this particular 2s electron, it will get excited and it will go into my 2p orbital. So whenever carbon is going to bond with 4 hydrogens, this electron, this particular electron, it will get excited, it will get energy, and it will go into the 2p orbital. So this will be called my excited state of carbon. So this will be called my excited state of carbon. So it will look something like this. This will be my 1s2 again, and this will be my 2s, and here I have 2p. Now 2s will, in 2s I'll have one electron only, because the other electron, it has shifted from 2s to 2p. So one electron here, one here, and one here. So this is my 2p, which is 2px, 2py, and 2pz. Now here we can see that this is the excited state of carbon. Carbon excited state. Let me write it down. This is the excited state, and this was the ground state. This was the ground state of carbon. Now whenever carbon will try to bond with hydrogens, generally hydrogen has how many electrons? Hydrogen, the electronic configuration of hydrogen is 1s1, and it will have only one electron in its 1s orbital. It will have one electron only. Now to bond with carbon, it can actually bond with 2s orbital and the 2p orbitals. But in this case, what happens is, this 2s orbital, which has one electron, and the 2p orbital, 2p orbitals, three orbitals here, which also has one electrons, they intermix together. What do I mean by intermix here is, this is my s orbital, this is my p orbital, this is my other p orbital, and this is my third p orbital. So let's say this is my 2s orbital, this is my 2px, this is my 2py, and this is my 2pz. They all intermix together and give me 4 hybrid orbitals. They give me 4 hybrid orbitals. What do I mean by hybrid orbitals here? So these all 4 orbitals will intermix together and give me my similar energy hybrid orbitals. The hybrid orbitals which are formed will be similar in energy, and it will have one electron each. So how will these hybrid orbital look like? The hybrid orbital will look something like this. It will have a bigger lobe. It will have a bigger lobe here. It will have a bigger lobe here, and here I have a smaller lobe. And this will be called a sp3 hybrid orbital. Why sp3? Because 1s and 3 p orbitals are combining to form a hybrid orbital. Not one hybrid orbital, 4 hybrid orbitals, which will be called sp3 hybrid orbital. So how many orbitals we got? We got 4 sp3 hybrid orbitals. 4 sp3 hybrid orbitals with equal energy. Now we know that 2s and 2p have some gap in energy. If I have to write, my 1s stands here in the energy. If I have to write energy, my 1s stands here, my 2s stands here, and 2p is somewhat on top of 2s, means there is a gap of energy here. But whenever these intermix together and they are forming hybrid orbitals, the hybrid orbitals will be of equal energy. So all the electrons will be of equal energy. And the sp3 hybrid orbital will look something like this. Now if I have to arrange these 4 hybrid orbitals in space, how will I do that? Because I need least repulsion for the compound or for carbon, these hybrid orbitals will arrange themselves by having maximum angles from each other. So I'll have one hybrid orbital like this. Let me draw it with the other color. So the other hybrid orbital something like this, and then one more hybrid orbital, and the last one. So the last hybrid orbital. So this will actually attain a tetrahedral structure. This will actually attain a tetrahedral structure where you can imagine there is something at the center, and these two things are in plane. One is actually coming out here and the other one is going in. So, and all the angles in this particular geometry is 109.5 degree, approximately 109.5 degree. All the angles are same and they are 109.5 degrees. So all these hybrid orbitals, they arrange themselves in tetrahedral geometry. And all these orbitals have 1 electron each. All these orbitals have 1 electron each, as we saw here. So I'll just show you that all these hybrid orbitals had 1 electron each. So all these hybrid orbitals have 1 electron each. Now let's come back to hydrogen. Hydrogen has 1s1. So in the 1s orbital only it has 1 electron. Now if I have to draw 1s orbital of hydrogen, so my hydrogen will bond. Sorry for this. Let me draw it again. So my hydrogen will bond with all these hybrid orbitals with 1 electron. So this is my hydrogen. The red color one is my hydrogen. I'll just write hydrogen here. Okay, so these hydrogens will bond with all these hybrid orbitals and they'll form a tetrahedral geometry. Now the question will be, why did I have to make hybrid orbitals? Why didn't the 1s orbital of hydrogen, it didn't overlap with 2s orbital and the 2p orbital? So theoretically, when we observe the bond angles of CH4, theoretically or experimentally, when we observed the bond angles of CH4, we found out that all the four bonds were similar. And the angles between all the four bonds were equal. That is not possible if we actually overlap the 1s orbital of hydrogen to 2s of carbon and the other 3 hydrogens to 2p. Now if carbon's 3p orbitals has to bond with 1s of hydrogen and 2s of carbon will bond with 1s of hydrogen, these bonds won't be equal. That's why the theory of hybridization came up, where we say that all these 4 bonds, they intermix together and they form 4 hybrid orbitals which are equivalent in energy. And the number of hybrid orbitals formed will always be equal to number of hybridizing orbitals. Here we got 4 hybrid orbitals, and the number of participating orbitals were how many? 1, 2, 3 and 4. That's why we got 4 hybrid orbitals. So this is how we determine the geometry of CH4. So CH4 will be a tetrahedral geometry. If I have to write CH4, I'll write it something like this. This is my hydrogens. Or I can, if you know the wedge and dash structure, I can write it something like CHH with 1 hydrogen coming out and 1 going in. So this is the geometry of tetrahedral or CH4. So this is the geometry for methane. Now in the next video, we'll look at the pi bonds and the other types of hybridization, which are SP and SP2. There are other types also, but in the next video, we'll look at the SP and SP2 types of hybridization.